Welcome back. This is Fundamentals of Micro and Nano Fabrication. My name is Sushobhan Awasthi from ISC Bangalore, and today we are going to talk about another additive processing step, specifically native oxide film growth. Native oxide is basically just referring to the fact that these are films that are directly grown from the wafer itself. So, the chemistry involves the wafer. So, wafer is one of the precursors of the reaction. So, the way to grow native film is the native film in silicon is silicon dioxide, and that is the most important insulator in semiconductor fabrication. It is used for several things, the most important of course being the gate oxide. So, if you look at this slide number 2, the most important is this gate oxide in field effect transistor. This is where silicon dioxide is used and used most successfully. But there are other aspects of silicon dioxide where silicon dioxide is used in common CMOS purification. We have already looked at how silicon dioxide, which was formed through chemical means, was used to do cleaning. Remember, we were forming silicon dioxides and dissolving into HF. So, that is one use. Then there are certain masking oxides. During diffusion, if you remember, we looked at how masking oxides are used to prevent or to dopant from diffusing through, and you can use that to create patterns. We have not discussed this because this is a device related issue, but you can appreciate that in a typical process you would need to insulate a device from another device. So even though the wafer is the same, the two devices need to be electrically insulated from each other, and we use field oxides to do that. So that is this oxide. Oxides are actually also used to insulate metal layers. So in silicon you don't just have one layer of metal, you actually have multiple layers of metals. And we will come to that when we do metallization, but each of those metal layers has to be insulated from one another. Imagine over bridges and under bridges on a road, the similar thing with metals. So those are back end metal oxides, so those oxide layer also are typically silicon dioxide. So you can grow silicon dioxide two which ways. So one is a thermal grown oxide and one is a deposited oxide. So this lecture is going to be about thermally grown oxide. So this is an oxide that is grown from the silicon wafer itself, and we will talk about the deposited one later. So this lecture, which is of grown oxide, is what is a native film, right? So why am I hyping up the silicon dioxide interface so much? In the introductory lecture I did briefly discuss this, and the reason for that is that this interface between silicon dioxide and silicon. So this is an amorphous film, this is a single crystalline film, and you would expect that this interface between the film would be fairly defective, because there is a transition that is occurring from a crystalline phase to a amorphous phase. This is, by the way, a TEM image. So these dots that you are seeing is the actual atoms, right? So you would expect some defects here, or in fact a lot of defects here, and this transition to be not very sharp. It turns out that is not the case. The transition is extremely sharp, and it's a few atom thick sharp, and the number of defects are very low, very low. So in fact this is the interface from a material perspective. Silicon dioxide interfaces are one of the best interfaces we know how to grow, and this is the reason why silicon is the dominant semiconductor. Gallium oxide, germanium, all of these semiconductors have been the materials of the future and will remain materials of future simply because they can't beat the quality that we can get from silicon dioxide interface. Only very recently have we actually started getting that good a quality of interface from gallium arsenide and some other semiconductors. So silicon dioxide, at least the crystalline version of silicon dioxide, which is quartz, is also a tetrahedral just like silicon. So silicon oxide bond is around 1.6 angstrom, and oxygen bond length is around 2.7 angstrom. But if you were to go back and compare this with the silicon lattice, you will see that silicon dioxide lattice is not matched with silicon lattice, and that is why you can't grow crystalline silicon dioxide on top of silicon. It is too large. The density of silicon dioxide, crystalline silicon dioxide, which is quartz, is around 2.65 grams per centimeter cube. What you end up actually growing is a thermal oxide, which is amorphous, which is significantly lower density. The structure maintains its tetrahedral unit cell, so you still have silicon and silicon dioxide and it's stoichiometric and everything, but it is not crystalline. So it has this sort of amorphous undefined crystal structure, but despite that its electrical properties are excellent, which is both a surprise and a happy surprise. So, what is the mechanism by which we do the crystal growth? So, since this is a native film, one of the precursors is the silicon itself. So, silicon is not coming from outside, silicon is from the wafer itself. So, silicon gets directly oxidized to form SiO2. There are two ways you can do that. The two ways are different in their in the oxidant that they use. So, one is called dry oxidation, one is called wet oxidation. The dry oxidation use oxygen gas. Now, this is the simplest thing you can arguably do, right? You can just expose silicon to pure oxygen, form silicon dioxide. The reaction is fairly simple. You need temperatures of around 900, 1100 degrees C to do this at a rate that is useful. Around 800 oxidation starts at very low growth rates. 900 it becomes reasonable enough. So, for most cases you need an oxide that is around 10 nanometers or 100 nanometers thick, which basically means at growth rates of around 0.5 to 3.3 nanometers per minute, you have a growth window of a few minutes to a few hours. Usually you don't grow above 500 nanometer thick films with this method because it's so slow. The quality, however, is excellent. This is the best silicon dioxide we can grow. So, for the best quality oxides, we use thermal oxide or dry oxidation. So, this is where the gate oxide, for passivation, for tunneling oxide, we use these. The wet oxide uses water as the oxidation source. The reaction again is fairly intuitive. The temperature remains the same. However, the growth rates are much higher. So, if you compare this to this, the growth rates are much higher. That allows you to grow much thicker film. However, the quality is a little poorer. So, it's not as poor as some of the other oxides that you know, but quality is definitely lower than dry oxidation. So, we use it for field oxide, for masking layers where the electrical quality is not that important. A few other comments I would like to make is that below 800 degrees C, typically the rate of oxidation is very small. This would be at odds because in the past I have told you that silicon will form a native oxide if you leave it in air. So, how is it that we do form a very thin silicon dioxide even at room temperature, but then I am claiming that you will not have any appreciable growth rate all the way to 800 degrees C? The short answer to this question is surface and bulk are different. All of these things that I am discussing are bulk properties. The surface is often has very different energetics. So, the top surface of silicon get oxidized even at room temperature and form a very thin layer of oxide. However, once that oxide forms, that oxide prevents the formation of more oxide, so you don't grow any thicker, right. So, in order to continuously flow an oxide film that continuously becomes thicker is not self-limiting, you need high temperature of around 800 degrees C. So, all this discussion leads us into the mechanism of silicon oxide growth. Silicon dioxide growth mechanism is one of the most studied and well understood mechanism, and the reason I would like to go into this into a little detail and a little slowly is because it's a very good case study of how such mechanism studies are done. So, if you understand silicon oxide growth, good, but more importantly try to appreciate the science behind it and how you can probably use some of these concepts in your own growth studies. So, fundamentally what is happening is the following: you have your silicon wafer and on top of that you have grown some silicon dioxide. So, let us say we started this process at t equal to 0 and we have suddenly started analyzing it at t equal to 10 minutes. So, by this time some thickness of silicon dioxide has grown. Above the silicon dioxide is your oxidation source. This can be water, this can be oxygen. For argument's sake, let us say oxygen. So, we are doing dry oxidation. Now, this dry oxidation precursor, in this case oxygen, has to reach this interface in order to interact with silicon. So, it must travel through the silicon dioxide through some mechanism and reach the interface where it will react with silicon to form silicon dioxide. Now, the only mechanism we know of pushing the material of one type of material through another material is diffusion, right. This is not an electrical species, we can't put electric field on anything, it just has to go by diffusion. So, that can be better represented with this graph. So, if you look at your oxygen species as a function of depth, you have some concentration in the gas. Now, because the oxygen is diffusing from top to bottom, you are getting some profile. So there is some depletion of the oxygen precursor in the gas phase. Then it reaches the oxide. Then there is a profile of oxygen species in the oxide. Now this is because of diffusion. So all the same mathematics of diffusion that we have read and understood apply. And finally it reaches silicon, at which point it will react with the silicon itself to form silicon dioxide. So this concentration N1 will be very low value. Right? Now of consequences are 3 fluxes, of which 2 are important. So the one flux is the flux that is within the gas itself. So the oxygen species is moving from this region of higher concentration to this region of lower concentration. It turns out that depletion is very minimal, that flux is very large. For the purposes of this discussion, let us ignore it. When we talk about chemical vapor deposition, however, this will become the dominant mechanism, but we will come to this at that point in time. For now, let's just ignore it. The other flux that is of importance is the flux of oxygen species within the oxide itself. So this is this flux, right? So F1. And then the last is the flux of the oxygen species reacting with silicon to form silicon dioxide. So that is this, that is happening at the interface. Now all of these fluxes are in series, and things that are in series must be similar, otherwise there will be accumulation. So if this is steady state, F1 must be equal to F2. Now let's look at that into a little more detail. So by the way, this whole kinetics is called the Deal-Grove model. I'll give the reference to the paper, the first paper that Deal and Grove wrote on this. If I'm not wrong, in fact, Grove went on to be one of the founders of Intel. So a very important man and a very important contribution. Okay. Now let us first assume a few things, because whenever you do modeling, you have to assume a few things. So let's assume the gas flow is high enough so that gas diffusion is not limiting, which is what I just said. Let's assume that this profile is very shallow, is not a problem. You can get arbitrarily high amount of the diffusion within the gas is very high, right? So this profile is very shallow. The second thing that you assume is N0 is just the solid solubility of the oxygen species in the oxide, because remember the same thing we did in diffusion. In order for a diffusion to occur, the species first has to get inside the material, but how much can it get inside the material is directly proportional to what is the solid solubility. So here we are talking about solid solubility of oxygen species in the silicon. So this N0 is nothing but the solid solubility of oxygen in silicon dioxide. So that's first assumption. Those are 2 assumptions. The next, let's just do the Frick's model, right? So this is diffusion, Frick's model applies. So flux F1 is nothing but given by the first law, which is d diffusivity of this oxygen species inside oxide, n by x, dn by x. Now assuming this is linear, and under very good approximation it is sort of linear, this is nothing but d into n0 minus n1 by x, where n0 is what? It is the solid solubility, and n1 is the concentration at the interface. The second flux we can assume to be a chemical reaction. So chemical reactions are either a first order chemical reaction, a second order chemical reaction. Let's assume here to be a first order chemical reaction. So there is a chemical constant K and multiplied by the reactive species. So this sort of is assuming that the rate of the reaction is completely decided by the oxygen species, and that is not a bad approximation, because you see silicon we have plethora of. There is a silicon lattice there. There are literally 10^22 silicon atoms sitting on the surface. The problem is not availability of silicon, the problem is availability of oxygen species. So the reaction rate does not depend on the concentration of silicon, it depends upon the concentration of oxygen. And what is the concentration of oxygen at the interface? It is N1. It is N1. So this flux F2 is nothing but the reaction rate constant K into N1. And as we have discussed, under equilibrium, these two have to be the same. So you equalize them, you can get rid of the N0, you can get rid of N1 as an unknown. N0 is known because this is solid solubility, and all of this math can be summarized in this model. So this, if you solve this exactly, you would get this expression, which is T0 ox square is equal to AT ox into BT. Now this T ox is nothing but thickness of the oxide. Okay, this T ox is nothing but the thickness of the oxide. Now if you want to calculate the thickness of the oxide, at a given time, all you have to do is solve this second order equation. So, this is a quadratic equation, it has a quadratic formula, you can easily solve to get an answer. But we can do little more, we can actually analyze this model little more in detail. So, let us look at the quadratic solution of this equation. So, the quadratic solution is Tox equal to this. Now, supposing T is small, which is you are looking at very short times, you are looking at at the start of this oxidation process. So, if T is small, then we can ignore this, and in which case Tox can be approximated as nothing but BIA into T. So, this term is too small. So, in this, so for very small times, the oxidation growth rate is essentially linear, right. So, the oxide film will simply linearly increase with time. So, that is why B by A is often called a linear rate constant. Now, if you take the other extreme where time is large, you are looking at growth rates for very long times. At that point in time, this term is now the larger term. So, you can ignore 1, and if you again solve it exactly, the T oxide will now is a parabolic relation with time. So, the oxide thickness scales with root of time. Here B is called the parabolic rate constant. Okay. Now, that is not all, we can go dig a little bit deeper, which will give us some insight into the mechanism. So, let us look at the linear rate constant, which is relevant at small t. If you measure the linear rate constant as a function of temperature. So, by the way, the graph that you are seeing is called an Arrhenius plot. It is often used in a lot of mechanism based studies. So, let us understand it a little bit. By convention and for ease, these plots are often plotted as a function of 1000 by T, which is Kelvin inverse unit. So, if T is in Kelvin, 1000 divided by T is what is this axis. You can of course convert this axis into temperature, something you more intuitively understand. So, 0.7 refers to 1200, around 1200, 1 refers to around 700. So, this is a decreasing temperature scale, right. If 1000 by T is increasing, then T must be decreasing. So, this is the high temperature end, this is the low temperature end. So, if you were to plot the linear rate constant as a function of 1 over T, you would get these linear curves, these linear relation. Let us first look at this linear relation for two different oxidation species. So, let us look at for water, right, this is wet oxidation, and once look at for dry oxidation where it is for dry oxygen. The first thing to notice is that the activation energy EA, which is the slope of these two curves, is exactly the same or roughly the same. This is 2.05, this is 2.00, that is important. The second thing that you would notice in this figure is there is a subtle difference in the absolute value between silicon 111 and silicon 100. However, the slope is the same. So, the slope is the same, but the absolute value is a little bit different. Now, can we explain this observation based on the model that we have just made? Now, first way to understand the model is to always compare it to something physical. So, this activation energy, now this is a fitting parameter right now, but can we relate this fitting parameter to something important? And we can realize that the energy to break a silicon-silicon bond is at around 1.8 eV. So, this value is fairly close to this, right? Now, does our mechanism support this? Well, let us look at it further. You see, if the time is small, then the growth is not limited by diffusion, right? What we are essentially saying is the time is small. If you go back, if the time is small, then this silicon oxide has not grown to a large enough thickness. If the silicon oxide has not grown to a large thickness, then the problem is not diffusion through the silicon dioxide. That is fast. The bottleneck is reaction with silicon. So, the problem is not F1. F1 is fast, but the problem is F2, but because in equilibrium the two must be equal, F1 must be equal to F2. So, the concentration gradient changes such that F1 becomes equal to F2. So, coming back to that old slide of mine, yeah. So, the growth rate is not limited by diffusion. The diffusion of oxygen species is not the problem. The issue is rate of reaction between oxygen and silicon. So, this linear rate constant must be proportional to Kn naught. right, where K is the reaction, the rate of reaction, the constant of reaction rate between silicon and oxygen. So, if that is the case, then EA, the activation energy for this process, must be related to silicon-silicon bond energy. It is no surprise that this 1.83 and 2.85 are similar, because in order to do the oxidation, what do you need to do? You need to break the silicon-silicon bond and form the silicon-oxygen bond. It is no surprise that this EA is the same for wet and dry oxidation. It does not change whether the oxygen species is water or the oxygen species is oxygen, because in both cases you are limited by the ability of silicon-silicon bond to break. So, the oxidant does not matter. What you are oxidizing? Silicon. So, the energy of breaking that bond is the bottleneck. So, that also makes sense. That was also consistent. And then how can you explain that the rate of reaction is actually dependent upon the orientation? Well, that is easy to understand. You see, the average number of bonds that you see at the interface depends upon orientation. We looked at this when we did crystal growth. So, simply because the number of average bonds the silicon 100 phase has versus silicon 111, it is easy to imagine the energy it will take to break those bonds will also be different, and that accounts for the small difference in the absolute value. However, their temperature dependence will not change, right, because the temperature dependence depends upon the activation energy. So, all of this observation can be exactly squared with or explained by the mechanism, and that is the hallmark of a good model. All the data is explained, all the intricacies are explained. By the way, once again, all of this was done in this landmark paper. If you have not read it, I would urge you to go and look at this paper. It's a very old paper, 1960s if I am not wrong, but very, very, very convincing paper. So, this we have all done for linear rate constant. Now, can we do a similar sort of analysis for the parabolic rate constant? So, we can. So, here is the data for the parabolic rate constant. Once again, we are plotting it on an Arrhenius plot. So, the temperature is in a decreasing scale, and you are plotting it for 1 over T or inverse temperature scale. So, once again, we are doing it for two different oxidation species. One is wet oxidation, which is water. One is dry oxidation, which is oxygen. And here, unlike the previous case, we do measure a different activation energy. However, we do not measure a change in orientation. So, I have only plotted it for one curve because there is no difference for 111 and 100, unlike the previous case. So, now can we explain all of that data? We can explain all of that data by again comparing it with known values. So, if you compare this activation energy, so let us do the same analysis for the parabolic rate constant. So, once again the parabolic rate constant is plotted on this Arrhenius curve. So, we are plotting the constant as a function of 1000 T, 1000 over T. Just to help you along, there is a temperature axis on the top, right. So, you can sort of understand. So, this is decreasing from 1000 to 600 degrees C. We are doing this analysis again for two oxidation species. One is the water and one is dry oxidation. Now, unlike before, in these two cases, we do measure a different activation energy. So, these activation energies are different, right? They are not the same. Now, can we square that with the model? We can. So, let us compare that with the activation energy for water diffusion in silicon dioxide. So, that value is 0.79. So, see how close that value is to what we measure. And then we also know the activation energy for oxygen diffusion in silicon dioxide, and that value is 1.18, and see how close it is to the value we measure here. This is giving us a hint. This is telling us something about the mechanism. What is it telling us? Well, you see, parabolic rate constant is relevant for large thicknesses of silicon dioxide. So, if the silicon dioxide thickness is large, now your growth rate is not limited by the reaction rate. So, the reaction rate is not the problem. The problem is now the diffusion. You are unable to get your oxygen species through the very thick silicon dioxide and make it react at the interface. So, not by reaction rate, but by the rate of diffusion. So, if you are limited by the rate of diffusion, it only makes sense that the activation energies that you measure must also be the activation energy for that diffusion mechanism. So, yeah, this all makes sense. So, B, which is the parabolic rate constant, is proportional to D into N naught. So, it depends upon the D. So, the activation energy of B must be the same, the activation energy of B must be the same as activation energy of D. That is not all. You see, because this is diffusion, and this is diffusion is happening on silicon dioxide. Remember, silicon dioxide is amorphous, right? Whether silicon is 111 or silicon is 100, the silicon dioxide on top is amorphous. So, if it is amorphous, it stands to reason that irrelevant of what is the substrate orientation, the diffusion will be the same in silicon dioxide, right? If the properties of silicon dioxide are not changing, why will the diffusion coefficient change? So, it makes sense that there is no crystal orientation effect. 111 is the same as 100, unlike before where crystal orientation mattered. So, all of these things are consistent with the model. All of this was once again in this paper. I urge you to read it if you have not done so. So, there is one problem, however. You see, which diffuses faster, water or oxygen? If you go and look at the values, it turns out oxygen diffuses faster in silicon dioxide than water molecules. So, if that is the case, then how is it that wet oxidation grows faster than dry oxidation? So, if the problem is diffusion and diffusion of oxygen species is more, then the growth rate of oxidation with oxygen should also be higher, but that is not the case. So, look at these values, right. With dry oxidation, the parabolic rate constant is lower, the growth is slower with oxygen than it is with water. So, how is that possible? So, that actually can be explained only if you go into a little bit more detail, right. So, that is this slide. So, let us look at this diffusivity. So, here is a chart of diffusivity of oxygen and water as a function of 1 over T. So, this is also an Arrhenius plot, and this is what I am talking about. You see the absolute value of D for oxygen is higher, this is higher, this is lower. So, the way we can explain this is by looking at this figure. You see what is happening? What is happening is that you have some concentration of oxygen species in the gas, that does not change, but then you have certain solid solubility, right, you have certain solubility, and depending upon what solid solubility you have, then you have a certain gradient of oxygen species inside your silicon dioxide, and then it reaches silicon, and this is this oxygen that is then reacting at the silicon dioxide interface to form your oxide. Now, when you are doing diffusion, two things matter. One is diffusion coefficient, and the other is gradient. What is gradient? Gradient is simply the change from this high concentration to this low concentration. This is dN by dx, right. It so turns out that even though the diffusivity of oxygen is higher in silicon dioxide, the solid solubility of oxygen is not higher. So, the solid solubility of oxygen in silicon dioxide is only 5 into 10 to the power 16, while the solid solubility of water inside silicon dioxide is around 10 to the power 19. So, this is 1000 times higher. So, if you look at the concentration gradient, this value which is C naught, which is the peak, right, the peak is much higher with water than the peak is with dry oxygen. So, even though the dry oxygen diffusivity is faster, but the peak is lower. So, the profile of oxygen species is much shallower with dry oxygen than it is with water, and that is what allows you to explain why the oxygen species, this value, see what matters is this value, because this is what is the bottleneck, this is what will create your silicon dioxide. The availability of this oxygen species at the interface is higher with water than it is with dry oxide, and that is what explains your higher growth rate. Okay. So, a good theory is always one that sort of explains all the data and is consistent with all the data, and the growth of silicon dioxide is a very good example of a good theory that has been backed by data and accepted. So, whoever of you wants to do these mechanistic type of studies of growths, I think should read and understand oxide growth, because oxide growth in my opinion is a beautiful theory, a beautifully written paper that sort of captures everything in a very consistent and elegant fashion. So, with that actually I will come to an end. We will just leave you, with that we will come to the end with this lecture. In the next lecture, we will go into in little more detail of silicon oxide growth. We will look at some equipment, we will look at some advanced concepts like ultra thin oxides, we will look at defects, and yeah, so see you next time.